Give me 1 second to kind of grab the test. 2015. Where's that? Okay, this is 2007.
Nice.
Hi guys. All right. Prepare your files for the 2007 and 2015. We're gonna take a look at those two files. ICQ. Okay.
Teacher, I'm at my grandparents' house and I forgot to bring the 2015, so maybe
You
I will just look at my PDF file.
Yep. It's okay to take because you fill in the form, right? So you know like which question you did not answer correctly. So you just need to take a look at the PDF file to follow with me. Okay. All right, I'm gonna share the screen now. Let's take a look at 2015 first. All right. Can you see my screen now? Hello?
Yes.
Okay, good. All right, we're gonna start with 2015. Let me see the question that you request for this one. Okay, we have 5, 6. Okay, wait, five. Okay, 5, 6. Question number 5 first. Um, hydrogen. Hydrogen is the first element in the periodic table. The atom also the lightest, account for 88 of the atom in the known universe on young stars fueled by hydrogen. The atom fused together in a nuclear reaction to make helium. Hence, hydrogen is the most abundant element in our solar system. Um, most abundant element on Earth by mass. Hydrogen gas when ready and oxygen give out the heat. The reaction forms water. This is why mass blah blah blah. Okay, so they give they basically give us a bunch of information. Um, so based on the given information, which of the following statements is correct? Is correct. Okay, oxygen is the most abundant by in ocean by mass. Um, do we have that information here? 10 most by mass. Okay, we're gonna. Oh, wait, take a look at here. The reaction form water, which is H2O, which is why by mass, hydrogen is the second most abundant element in the ocean. Okay, take a look at here. For every 2 hydrogen, we have 1 oxygen, right? So every 2 AMU of hydrogen, we're gonna have 16 AMU of oxygen. Okay, so if hydrogen is the second most abundant element in the ocean by mass, then oxygen must be the most abundant element by mass in the ocean for sure, because um, the mass of oxygen is like 8 times more than the mass of hydrogen. Get it? So the first one is the correct one. Okay, take a look at the second one. The majority of hydrogen in the solar system is found as water on the planet. This is not correct. Um, water is like the main, maybe the main form on Earth, but in the universe, um, it just say it's just that we have hydrogen in young star, and we have hydrogen atoms in the known universe. All right, so it's not going to be found at war on the planet. Not in the solar system. No, no, in the solar system, it's going to be found at the atoms in the universe, not war on the planets. The heat given out by a star is due to the combustion of hydrogen gas. No, the heat that is given out by a star is a nuclear reaction. Okay, nuclear reaction to fuse two hydrogen atoms together to make helium. The combustion reaction of hydrogen is the reaction to form water on Earth. All right, this is the reaction to form water on Earth. Okay, so this is not correct. The nuclear reaction in stars produce helium and water. Okay, just helium, not water. Okay, not water. So the correct one is A. Um, Moving on to the next one. Also, make sure that when you answer the question, try to do the questions on your own one more time. Okay. Oh, what? This is the list. Okay. Give me one sec. Okay. Moving on to the question number 6. Oh, number 7. Second and 7. 6. Mhm. The diagram. This is the diagram to showcase the boiling point. All right, the boiling point of all gases on Earth. Um, 78% of the gas volume of air is nitrogen, 21% of oxygen, and the remainder is trace amounts of other gases. Okay. A sample of air was cooled down to a certain temperature. As a result, the volume decreased by almost 22% as gases condensed. The temperature of the cold sample could be what? All right. So 22%. Um, the volume decreased by almost 22% as the gases condensed. So take a look here. 22 is almost equal to 21 plus, the trace amount. So it's almost 22. So take a look at the diagram. Nitrogen is like below, nitrogen is below um, oxygen. So here, if you set the temperature to be around here, you're going to have 78% of nitrogen. All right, neon or some other gases, they are just trace, so you don't really have to care about them that much. And the rest will be here. Most of the gas will, the other majority of gases can be found in oxygen. All right, um, so we're gonna take a look at all the things that we have here. So um, okay, so if the temperature is set at minus 100 degrees Celsius, which is around here, you can see that nitrogen and oxygen, they are all liquefied, right? They are all liquefied, and therefore the volume will decrease um, by almost 0%, right? Because you have to start from here. You have to start from the air, which is over here. We have just the air over here. If you lower down the temperature to around 100 degrees Celsius, which is here, right? So it means all the gases are in the gaseous state, right? None of the gas is liquefied, and therefore the volume uh, will decrease by almost 0%, right? So at 100 degrees Celsius, it will decrease by almost 0% because none of the gas is liquefied. If you set the temperature to minus 160, only krypton and xenon will be liquefied, all right? So the volume of the gas will decrease by probably less than 1%. Why? Because krypton and xenon will be found in the atmosphere in trace amounts, right? So it would be less than 1%, all right? So see here, this is the sum of like 21 and some other, you know, some other percentages. So it must be like between nitrogen and oxygen here, so that when you set the temperature to be around this temperature, it will um, condense xenon, krypton, oxygen, and argon, right? The whole thing together will add up to around 22%. And you basically kind of condense the gases out the air. So it will be decreased by almost 22%. So it must be in the middle between nitrogen and oxygen. So it must be minus 190 degrees Celsius. If the temperature is below minus 200, which is below um, the boiling point of nitrogen, the nitrogen will also be condensed, and therefore it's going to add up to um, the volume of the air that we lose in the end. So it's going to be 80, 78 and plus 21 plus the percentages. So it will almost 100%. Okay. You set the temperature to be this temperature is going to be almost 100%. Okay, moving on to the question number seven, right? I guess. Okay, number seven. A saturated solution is no in which no solute will dissolve. A student wanted to make two saturated solution. One sodium chloride, the second is silver nitrate. All right, sodium chloride is NaCl. Silver nitrate is AgNO3. Um, we're gonna use this much of water. Sodium chloride is less soluble in um, than in the water than silver nitrate. Okay. We use the same amount of volume for each of the solution. Sodium chloride is known to be less soluble than silver nitrate. And then they ask if 22.8 gram of sodium chloride dissolve in the first sample of water, what mass of silver nitrate should dissolve in the other sample of water? All right. So because silver nitrate can be dissolved. It can be dissolved. It is more soluble than sodium chloride, right? So if you can basically dissolve the whole thing of sodium chloride that we have here, then the amount that we can dissolve for silver nitrate must be more because the solubility of uh, silver nitrate is higher than the solubility of sodium chloride. So the answer is C, more than 28.8 grams. All right, set number 7, 8, 9, 10, 11. 8. Sodium chloride salt um, is added to water. Salines can be formed. Saline solution is basically the solution of sodium chloride, which is NaCl. The a small amount of carbon is mixed with molten iron. A form of steel can be made. Iron plus carbon, steel to form steel. Steel is like a mixture of carbon and iron. This is not a chemical reaction. This is a physical. Um, this is a physical process. All right. This is a physical change. You basically add sodium chloride to water, so it's gonna make a mixture. You add iron to carbon, and you kind of like you melt them and you kind of mix them together. So it's gonna give you a mixture. Mhm. When a small amount of zinc is added to copper, the alloy is known as brass. So brass is also a mixture between zinc and copper, right? All the example are the type of mixture that you can see here. The relationships about salt to saline solution is what to what? Okay, so sodium chloride is added to water, saline solution will be formed. So when you have a solution, water is the solvent, which is the one that we have more, and salt is the solute, which is the one that we have less than the solvent. All right, the amount of solvent is usually more than the amount of solute. So it means if only a small amount of carbon is added to iron, then carbon must be similar like a solute that would be mixed in the solvent, which is molten iron. Okay. And also the same for zinc and copper. Only a small amount of zinc is added to copper, so zinc will be similar to a solute and copper is similar to a solvent. Usually solvent is more than a solute. Okay. So based on that, if salt to saline solution, salt is solute, saline solution is the mixture. Okay, the mixture. So it's basically like the solute to the mixture, not to the solvent. All right, solvent, for example, like molten iron is a solvent, but steel is the name of the mixture. Okay, so saline solution is the thing that we need to compare to, which is a solution, a mixture already. So it can be like carbon to steel. This is correct. Carbon to steel. Carbon is the solute. Steel is the name of the mixture. Iron to steel. This is not correct because iron here is considered as a solvent to a mixture, so it's not correct. Carbon to zinc, they are not even related, so ignore that. Copper to brass. Copper is the solvent. Brass is the mixture. No, this is not correct. So 8A. Question number 9, 10, 11, 9, 10, 11. All right. So for 9 and 10, they are together. Mix exactly 10 milliliter of sodium chloride solution with exactly 15 milliliter of hydrochloric acid. Um, Sodium hydroxide is NaOH, hydrochloric acid is HCl, um, only salt and water. A student then heated the solution to get a solid. Which of the following pieces of laboratory equipment would be least useful for this experiment? Okay. Okay, let's take a look at all of them. What is a tripod? I think that you do know what tripod is, right? Is that is like the two it have the shape like a ring like this and it have two kind of like legs. Sorry, three legs. Sorry, I meant not the two. It's a tripod, so it must have three legs. All right, yeah, right, three legs. And this one is like you can think of a stove. All right, when you cook with the stove, there will be something to hold the pot just above the stove. All right, so it's going to be the same here. In the lab, when you want to heat up something, you're going to have something to hold it up so that you can have a burner below, right? So this is what we call a tripod. You just basically put the thing that you want to kind of like burn or the thing that you want to kind of heat up on top of the tripod so that you can have burner down below and heat it up. All right. So this one is useful, right? Because they specifically said that they still need to heat up the solution. All right. If you want to heat up, then you need to have a tripod. All right. And on top of the tripod, you can have an evaporating basin. Basically, it's like you can think it as like a pot, all right, or something like that. That can be used to kind of store all the solution that you have, and then you put it on the tripod to kind of evaporate, heat it up, and evaporate all of the water. So this is also useful. All right, measuring cylinder. That is to use to take 10 milliliter or 15 milliliter, all right? That is going to be this one, measuring cylinder. I think that you do see at home, like when you want to measure a certain amount of water for baking or something like that, you're going to see like this cylinder, um, this cylinder container, all right? And we have some marker on it to kind of signify the volume that you're gonna take. So measuring cylinder is to measure the volume. So this is also useful. We don't actually need the thermometer. Why? Well, actually, when you want to evaporate um, water, then you just need to bring it to a boiling, right? Bring it to a boil, not a boiling. Bring it to a boil, all right? Heat it up until you see boiling, and you're gonna leave it that there for a while. When the process stops, then you can adjust the solid. All right, so you don't have to really care about the temperature. No, you don't want to care about the temperature. You only care about whether you can boil it. You can bring it to a boil and then evaporate all the water. Okay, so this one is not really necessary. Question number 10. Mix exactly 15 milliliter of each of the two solution. The second student mixture will contain what? Okay, okay, take a look here. If 10 milliliter of sodium hydroxide and 15 milliliter of of hydrochloric hydrogen solution are mixed, they can only contain water and salt. It means if 10 milliliter of sodium hydroxide and 15 milliliter of hydrochloric acid are mixed, we're gonna have this reaction, and the reaction will be complete. All right. This is the reaction between sodium hydroxide and water. This is what we call a neutralization reaction. This is an acid. This is a base. All right. The way that you write out the reaction like this is a double replacement reaction. All right. You just need to switch the cation and the anion. Okay. Sodium is Na plus. OH is OH minus. Hydrogen is H plus. Chloride is Cl minus. So just switch sodium here with the hydrogen over there. All right. So sodium will come and combine with chloride. Hydrogen will come and combine with OH, and then you're gonna have the reaction. Okay. It means like for based on the information that we have, 10 milliliter of sodium hydroxide will react completely with 15 milliliter of hydrochloric acid. Then, if you use if you increase the amount of sodium hydroxide to 15, then uh, sorry guys, some of you did not turn off the mic. Can you do that for me? Okay. I'm going to continue. If you increase the volume of sodium hydroxide, then sodium hydroxide will be in excess. All right, it will be in excess, and therefore it will remain after the reaction. Hydrogen hydrochloric acid will react completely. That one is the limiting reagent. Okay, and therefore what you have after the reaction is the salt for sure, because you formed that water. Okay, and also sodium hydroxide that is in excess. All right, water, salt, and sodium hydroxide. So for question number 10, it's going to be A. All right, let's move on to the next one. 11. Okay, 11. Which of the following would not involve the Maillard reaction? Maillard reaction. Okay, so we have to take a look at what is in here. Making good quality coffee involves many different processes, including both physical changes and chemical reactions. Coffee has about 500 flavor compounds that have so far been identified, with about 60 that are important for taste. Maillard reaction described in food chemistry high temperature food processes such as roasting coffee. Okay, onto chemistry of coffee being more high temperature, longer roasting can be. All right, we have this step roasting. All right, heat up all the coffee beans, grinding up. So it's gonna be like you're gonna use a machine. to kind of like crush all the roasted coffee beans. Add a lot of hard work to dissolve the soluble chemicals. Okay, what of the following would not be involved in the Maillard reaction? Roasting potatoes. Which the following would not involve the Maillard reaction? Bread, baking, making toast. Okay, so for a Maillard reaction, that is the term when you treat the food with high temperature, right? Based on the information that you have here, that is a process to treat the food with high temperature. Making ice cream, we're probably not gonna treat it with high temperature, right? Because you're gonna need to lower the temperature down. Okay, so that is probably the correct one. For the other option, you can see that roasting potato, breast, baking, or making toast, they involve using high heat to cook the food. All right, so if they are gonna um, they're gonna involve the Maillard reaction for sure. All right, moving on to question number 15. Oh, 13 first. 11, 13, 13 here. Let me double check one more time. Question 10, 11, and 13. Okay, 13. One can tell which is chlorogenic acid, but this is a chlorogenic acid. During the roasting process, chlorogenic acid degrades into quinic acid and caffeine. Uh-huh. All right. This one, when you roast coffee, when you treat it with high heat, it will be decomposed into quinic acid and caffeic acid. During the reaction, there is a gain of what? Um, okay, take a look at here. Chlorogenic acid, which is C16H1809. All right. Um, quinic acid is C7H12O6. Caffeic acid is C9H8O7. Mm? So let's add up together. 16, that is equal to 7 plus 9. So the number of carbon is the same. All right. After the reaction, number of carbon is equal to the number of carbon in the first place. Moving on to hydrogen. 12 plus 8, then it's going to be 20. So we have only 18. So there will um there's a gain in two hydrogen atoms, right? Okay. Moving on to oxygen, 6 plus 4, so it's 10, and we have 9 here, so there is a gain in one oxygen atom as well. So question number 13, 2 hydrogen, 1 oxygen. Okay. D. um 15, 16, and 17. 15. Okay, so we have ice, which is a solid form of water. Scientists identify 16 crystalline form of ice. Some occurring naturally, other produced in the laboratory. Okay, so they are like different forms of ice. Snowflake are called hexagonal ice, or uh this is LH. Yep, LH. Small crystal that form the cloud, cubic ice. And then at 0 degrees Celsius, pure water has a density of this one. That means that 0 degrees Celsius, each milliliter of liquid water weighs this much. Only solid substances that have lower density of water will flow in it. Those that have higher density will sink. Okay, understandable. Below the All right, so below we have some of the density of water. Um, so liquid water, pure water, will have the density of 0.9999. All right. If you have higher density than this, it will sink down to the bottom. If you have lower density than this, it will float to the top. Based on the given information, which of the statement is correct? All forms of ice crystal will float on water. This is which is incorrect, right? Some of the crystals heavier than water. So it will float to the it will sink to the bottom. No, this is not correct. All right, moving on. 1 gram ice two here weighs more than 1 gram of ice 1H. It's the same, right? They are the same. When you talk about the weight, 1 gram of this will be equal to 1 gram of that. The only thing that is different is the volume. All right, is the volume. If you have 1 gram of ice two, and I want H. Where's I want H? I think I should. That is this one. Okay. You see, they are of different density. All right. So you have the same mass, but like you have different density, then the volume will be different. All right. Um, I2 has higher density, therefore, with the same mass, it will have a lower volume, right? Because the volume is equal to mass divided by density. And you can imagine like the mass stay the same. And basically, you increase the density, then the volume will be higher. Different ice forms are created by different types of water. I don't think that we have that information. I is solely for word. They are all word. Okay. So yeah, they are all word, but like in different setting, it will give us different crystals. So this is incorrect. 1 milliliter of I2 weighs more than 1 milliliter of ice 1H. Um, which is true, right? Because a ice two here it has higher density. So with the same volume, the one with the higher density will give you more mass. This is correct. 16, 17. 16, 17. All right. Okay, 16 and 17 is gonna be the reaction that you uh wait, do you have you learned this type of reaction? Oh, hmm. This is the reaction that you have to learn. Okay, you haven't learned this one. You gotta learn this kind of reaction again. This is how you extract iron from the hematite ore, which is Fe2O3. Okay, and the concept of um, this is called the blast furnace. The concept of this is that you're gonna mix the hematite. The main ingredient of hematite is Fe2O3. Coke is carbon, and limestone is calcium carbonate. All right. So you have that. Basically, you're gonna blow hot air on into the blast furnace so that you will burn carbon in oxygen to form carbon monoxide. That reaction will heat up that the reaction will release heat, right? It just imagine like how you burn carbon in oxygen, all right? That reaction will release heat, all right? And um, so the heat will facilitate the reaction between carbon monoxide, which is CO, and iron ore, which is Fe2O3, and it's gonna give you carbon dioxide and iron. So this is the reaction that you extract iron out of the iron compound. All right, and then also you have silica in as one of the impurity in hematite. You're gonna eliminate that using limestone, which is another material that you put in, so that it's gonna form slag. All right, slag is something that we float to the top of the blast furnace. It's not to the top of the blast furnace, but like you can see here, molten slag is going to be on top of molten iron. All right, so it's going to separate two layers, and then you're going to have one layer to extract molten iron. The other layer will be slag. All right. So in the reaction two, the iron compound is combined with another element. That what element is that? Well, it's oxygen, right? It's oxygen because based on the information that you have, um, carbon monoxide will be turned into carbon dioxide. All right, so it will gain one more oxygen atom. So it iron compound must combine with oxygen. All right, but you can also learn about this one again. Hematite, we have the chemical formula of Fe2O3. So it must be oxygen. Question number 17. Um, what the purposes of adding limestone is? Well, you see, you add limestone to eliminate silica, which is one of the impurity. So, yep, that is to remove one of the impurity in the iron ore, right? I think it's already provided here. Hematite is a mixture of iron containing silica. All right, silica is basically one of the impurities that we don't want. This is the process to extract iron. All right, so we basically don't care about silica. So you're gonna add limestone to eliminate one of the impurity. All right, 16, 17 already. Uh, Let me double check to make sure that I cover everything. Okay. So now we're going to move on to question number 22, 23, 24, 22, 23, 24. All right. Nobel Prize in 2014 was awarded to these people who were found to find a way for optical microscopes that can see beyond the theoretical limit, improve the understanding of molecule. All right. So we have these pieces of information. This one established the Albi diffraction limit, right? This one is the limit. And the side which is smaller than this limit is the optical microscope. Um, that is basically the smallest limit that we can see molecule clearly. This one demonstrated the outer microscope that could see a clump of particles that was small as 4 nanometer. 4 nanometer, which is around here. Um, Ernst Ruska developed an electron microscope, used electron instead of light, and this technique was improved by Binik and Heinrich Lohert to develop scanning electron microscope. This type microscope subsequently improves provide the image of individual atoms. So individual atoms is like below from 1 nanometer below, right? This is 4 nanometer. All right, which is true. Electron microscopy had allowed scientists to see small objects more clearly than light object microscopic. Yes, when you have electronic microscope, you basically kind of like push the limit away from the Abbe diffraction limit, right? Now you can basically see the smaller things on the scale, all right? So before you could only see like something that is larger than 0.2 micro meter. Now when you use the electron microscope, you can see further than that to individual atoms, which is much smaller than that limit. So that is correct. Um, Moving on, Richard's Zygmundi microscope could not see objects that is smaller than Abbe diffraction limit. Richard's okay, this is ultra microscope that could see at 4 nanometer. 4 nanometer is here, which is smaller than the limit. So this is incorrect. 2024 Nobel Prize awarded to Nitaly create images of atoms. Um, New techniques. They just find ways to improve the optical microscope. It's not new, all right? It's not new. They just find like a way to improve it. It's not new. So this is incorrect. Scientists have been able to see images of atoms for over 100 years. All right, to able to see atoms individually, it started in 1981, so it's not even 100 years. So incorrect. So the answer is A. 23. A myth circulating around the internet that you can get lead poisoning from lipstick. Many poisonous chemicals, there are traces of lead in the air, water, and soil. There's most amount of lead in the food that we eat. On average, there is approximately 1 micrograms of lead in a liter of lipstick. This level of exposure is not danger even a lifetime using lipstick. What could be likely the total mass of lead that a person may be exposed if they use 60 liter of lipstick over their lifetime? Okay. Um, 1 milligrams of lead can be found in 1 liter of lipstick. So if you use 60, then they probably gonna find 60 milligrams of lead, right? 60 milligram is equal to 0.06 gram of lead. So which is the answer is B. All right, you do the unit conversion as well because this is in gram, but the unit that you have here is milligram. Hmm. 24. Yeah, 24 and then 30. 24. This one. Um, okay, this is all the thing that we need to have rusting. So keep in mind that rusting is basically the process, the reaction between iron and oxygen to form Fe2O3. And there are two conditions for rusting to happen. All right. The first one is the presence of oxygen. The second one is the presence of water. Okay. So if you want to have rusting, the hypothesis is that iron and nitrogen alone won't cause rusting. Water is needed as well. Uh, so to test this hypothesis, then you need to have two conditions, right? You need to have two conditions. You need to have iron and you need to have nitrogen. This is the hypothesis, so it can be correct, it can be incorrect. All right, so you don't know. The condition that I gave you here, oxygen and water, they are like the conditions that you need in real life. But this is the hypothesis that we have an iron and nitrogen alone will not cause rusting. Then you need to include iron and nitrogen in one of the sample for testing. All right, so if you have just nitrogen and iron, then you don't see anything. All right. So we have another sample with iron and nitrogen and also water. All right. So now you have two samples, one with iron and nitrogen, and the other sample is iron with nitrogen and water. Okay. So if the hypothesis is correct, then this one will give you no rusting. And if the hypothesis is correct, then the second one will give you resting. Okay, so that is the hypothesis that we need to test. So question number 24, we gotta go with C, 5 and 6. Okay, if you use air or you use oxygen, it's not gonna be the thing that we want for our hypothesis. Hypothesis is the thing that you want to test. Okay, that you want to test. So it can be correct, it can be not correct. In this case, obviously it's not correct, but it's the hypothesis that we propose. So we want to test with nitrogen. So we are not going to use oxygen. We are not going to use air because in the air you have nitrogen, you have oxygen. So if you see the formation of rusting, you cannot be sure that it was because of nitrogen. It was maybe because of oxygen as well. So this is they cannot be tested. They cannot be tested. So the answer here is nitrogen and 5 and 6 only. Question number 30, which is the last one. Magnesium, 1 gram magnesium placed in a crucible, 20 grams set on fire with Bunsen burner. Once the reaction was well underway, a lid was placed on top. When the reaction had finished, crucible content has cooled. The crucible was again weighed without the lid at 0 zero point 0.7 grams of oxygen react with magnesium. After the reaction, the mass of weight crucible and the content would be expected to be what? All right. So we have magnesium, we have crucible. So 20 plus 1 we give you 21 grams. Uh, this is the mass of magnesium and the mass of the crucible, right? Crucible. And then when you finish the reaction, you wait without the lid. So 4 grams here will not add up to the mass that you measured, all right? And magnesium will react with oxygen to form magnesium oxide. So you basically, this is the reaction that is similar to the process of gaining oxygen to the mass here, all right? And you basically react with 0.7 grams of oxygen. So basically here you're gonna add 0.7 grams to the mixture between magnesium and the crucible, right? So it's going to be 21.7 grams of magnesium oxide, magnesium and the crucible, all right? So it's going to be greater than 20 grams, right? It's going to be greater than 20 grams. It's going to be 21.7 grams. That is the mass that you're going to expect. Okay, we have finished this one. Let's move on to 2007. Okay, let me take a look at the question that you request for 2007. Okay, let's see. Give me 1 second. Give me 1 minute. I need to take a drink. All right, moving on to 2007. Okay, let's take a look. Hmm. We have question 468, 4, 6, 8, 9, 10, 4, 6, 8, 9, 10, 12, 13, 14, 23, and 27. Okay, good. 4. All right, we have this setup. Lime water is clear and colorless solution that goes milky if carbon dioxide is CO2, is bubbled through it. A student is going to use the apparatus shown on the right to demonstrate why air breathed out contain a large quantity of carbon dioxide. To this, what should be done? All right. So you need to blow basically what is in our breath into lamp water. So it must go into the solution. All right. It must go into the solution. So you're gonna blow from here, and all the air from our breath will, will go under. All right, under the lamp water. So it's gonna improve the contact. If you blow from Y, then it's gonna be on the surface of lamp water. It's not gonna be in the solution. Therefore, it's not going to be efficient. Um, and then um, if you blow from X, then to kind of like um, to kind of equilibrate the pressure, because you blow the air in here, then you have to suck up the bubbles, the remaining gas, right? Because only CO2 will react with land water. For the other gases, they will be gas and they will fly up. Therefore, you have to suck up all of those gases out to kind of like maintain the pressure inside. If Um, if you do not suck out the other gases out the system, there will be pressure build up in this system and we can break the container, right? So you blow from X and you suck from Y, um, for C. Oh wait. C and D are both correct. Okay, so you need. Okay, now we have to take a look again. Um, blow into X, suck from. Oh, we have the word they in here, so it means C and D are both correct. Basically, they are of the same term, but the order is different. All right, whether you blow first or you suck first. Okay, let's take a look. Fresh air contain very little carbon dioxide. Oh, fresh air. Okay. You need to also test that fresh air contain very little carbon dioxide. Okay, I see. Sorry, my bad. All right. You have two hypotheses to make here. The first one is that the air contains just a little bit of carbon dioxide, but your breath will contain a lot of carbon dioxide. All right. So the first thing that you need to do is to suck up from tube Y, suck up from here. So that if you suck up from here, then it will suck the air into X and it's gonna bubble that amount of air into limestone. So that is the amount of air. Okay. And you will not see much of the formation of like cloudy thing going on in the land water because we don't have much carbon dioxide. All right. But after that, you blow from X, then your breath will contain a lot of carbon dioxide. It go into land water and it will bubble through land water, and you're gonna see the cloudy thing going on in the solution. So the first step is to prove that we don't have much carbon dioxide in the air. The second step is to prove that we actually have a lot of carbon dioxide in our breath. All right. If you do it the other way around, then you're gonna see the formation of white cloud in land water already. And then you cannot do the other hypothesis. You cannot test the other hypothesis. So you need to do it with the one that will not change the color of the land water, and then repeat that one again with the thing that you can probably see the change in color of the solution. Question number 6. If a container tap water is heated, some bubbles and brings blah 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 array, and then heat disappear. Right? What is the gas that makes the bubbles? Water vapor from evaporation of water, hydrogen gas from the water, oxygen gas from air that is dissolved in tap water. The answer here is D. Question number 6 is D. Okay. The thing is, in water that we do have like dissolved gas. All right, you have dissolved gas in that. One of the very example that you can understand is you know Coca-Cola or something like that, right? When you open it, you're gonna see some kind of sizzling like bubbles forming inside the bottle of Coke or soft drink, right? That is because you kind of dissolve CO2 in the bottle. All right, so it's the same here, but this is normal water. So we do have some amount of air that is dissolved in water. Okay, so when you heat it up, basically you have to talk about the solubility of gas. All right, solubility of gas will increase when the pressure increase. All right, and solubility of gas will decrease when the temperature increase. Okay, so when you heat up, usually when you cook, like when you want to boil water, when you heat up water, you're gonna see um at the very bottom of the container, you're gonna see some kind of bubbles. That temperature is not high enough. all right, for boiling, but you can still see some bubbles, right? When you heat up water, next time when you heat up water, take a look at the very bottom of the container. You're gonna see some bubbles, even though the temperature there is not 100 degrees Celsius. So there will definitely not boil. There will not be any boiling process going on there, but you can still see some bubbles. That is because the solubility of the gas will decrease when you heat up. All right, so these bubbles are going to be the air that is dissolved that are dissolved in water. Okay, so that's the because like after you eliminate all these bubbles, you cool it down and you reheat it, you see no bubbles because at that point you kind of eliminate all the bubbles. All right, all of the bubbles out the out water. So when you reheat it, it will not generate any bubbles. There is no bubble left. All right, in the water in the water. Okay, so if it is water vapor, then when you reheat it, there must be um, when you reheat it, there must be bubbles again, right? But now we have no bubbles, so it cannot be water vapor because water vapor can also exist in here or in here because it's basically water. Hydrogen gas or oxygen gas from water? No, because this is just to heat up, just simply heat up and cool down. So you cannot generate hydrogen or oxygen out of water. If you want to generate hydrogen and oxygen, the process that we use is electrolysis. Right? Electrolysis is the process to break down water using electricity to generate hydrogen and oxygen. Question number 8, 9, and 10. 8. What ions cause soap to form scum in seawater? And in seawater, we have ions of sodium, magnesium, calcium, potassium, and chloride. All right, we have these things. Um, and you have scum in seawater. So scum will form when you have uh, so take a look at only where you see scum and also where you have no scum. So you can kind of like eliminate the cause of sodium because if you have just sodium, potassium, chloride, then we have no scum. So you can eliminate sodium, potassium, chloride because you don't have scum there. Whenever you have the combination, whenever you have magnesium or whenever you have calcium, you form scum, right? So basically, magnesium and calcium are like the reasons why you form scum in seawater. So question 8 is going to be C. Because based on this one, you see no scum. So sodium, potassium, and chloride are probably not the main causes of scum. Question number 9. We have this graph. This is the oh, okay. This is the graph to illustrate the volume of water and the temperature. Okay. Which of the method CERN wanted to completely fill a 1 liter bottle exactly to the top with ice? Okay, with ice. Okay, this is ice. When you melt the water, the volume will drop. The volume will drop. It means the volume of ice is more than the volume of water, right? Which of the following methods will come closest to achieving this? You want to completely fill a 1 liter bottle exactly to the top with ice. Okay. Put crushed ice into bottle and shake it and press it down until the bottle is full. There will be some kind of space between all the crust. Fill the bottle with water from the tap water and put it into the freezer. Um, if you do this, the ice we explained it can break. It can basically break the container, so this is not useful. Okay. Fill the bottle with ice cold water and put it into the freezer. Okay, let's take a look at C is okay, but let's take a look at D. You fill it with crushed ice and then you add ice cold water until it's almost full, then freeze it. This is correct, all right? Because if you fill it with crushed ice, then between the crushed ice, we're gonna have some space. Then you're gonna add water, cold water to it. Okay, so you're gonna fill up all these spaces, and then you freeze it. You freeze it, then but it's almost full. Why? Because when you freeze water, the volume will increase. All right. So if you want to come exactly close to the top in terms of ice, then because you know that ice will expand in size based on this diagram, ice will expand in size. So you don't have to fill in water to completely full. You can only fill it to almost full, and then the ice will expand, and therefore it will occupy the rest of the volume. Okay, so this is correct. 10, 12, 13, 10. Okay. Do not is desiccant means silica gel that absorb water without becoming wet. While a package of silica gel. Okay, so usually when you eat food, all right, when you open a package of food like cracker or something like that, or even vitamin C, you're gonna see some kind of gel, like a bag of gels. All right, if you tear that bag out, that if you tear that bag, you're gonna see some kind of gel that is silica, and silica will absorb water. It will absorb the moisture in the air, so that the moisture will not wet the product. Okay. Um, while storing the silica gel, stop product from drying out inside the package. Attract and keep the prints. Prevent condensation of water inside the packages. Yep, it will prevent the condensation because it absorb basically desiccant will absorb all of the moisture. Therefore, you don't have water left for condensation, and then it will not wet the product that you have. So question number 10 is B. 12, 13, 12. Magnesia white powder of magnesium oxygen. Silica is another name for purified beach sand. Is a compound of elements silicon and oxygen. Hafnium is an element of foreign compound hafnia. HFO2 alumina is a white powder. All right, it's a compound. All right, alumina is a white powder from which element aluminum is made. Is a compound element aluminum, aluminum and oxygen. Okay, so based on the strength, magnesia is from between oxygen and magnesium. Silica is between silicon and oxygen. So if you end with the word A, it means you combine that element with oxygen. Okay. Um, 13 and 14. About 1/5, 20% of volume of air is oxygen. Calculated 24 liters of pure oxygen combined with 32 grams of sulfur when it's burned in. Okay, blah, blah, blah. What therefore would be the minimum volume of air that is required to burn 60 grams of sulfur? All right, 32 grams of sulfur will require 24 liters of pure oxygen, and pure oxygen, 24 liter of pure oxygen will basically um, account for like only 20% of the air. So 24 divided by 0.2, it will be, give me 1 second. So it's gonna give you 100, and so you need 120 liters of air for this. Okay, 32 grams of sulfur will be burned in 24 liters of pure oxygen. So, and this much of oxygen will account for only 20% of the volume of the air. So you probably need 120 liters of air. All right. Now you burn it. You you only use half of the amount of sulfur that you use in the first place. Now you only use 16 grams of sulfur. Then you're gonna need only half of the amount of air that you used to have. So it's gonna be only 60 liters. Okay, gonna be a 16. Um. Oh wait, minimum volume of air required. Oh, let me double check. 30. Oh no no no. Yeah, that's correct. 16. Mhm. Um, that's correct. Moving on to 14. Fuel contain these thing. Okay. Um, equal amount of heat obtained. All right, you're gonna have equal amount of heat by burning this much of methane, this much of propane, and this much of acetylene. All right, so it means you're gonna need the least amount of methane to basically give you the equal amount of heat to the other thing. Okay. When a fuels are burned, masses of CO2 produced are this one, and this one. Okay, so you're gonna produce this much of CO2, this much of propane, and this much of acetylene. So if you use the same amount of fuel, which one will release the most heat? Well, equal amount of heat will be produced by different masses of fuels. So if you use the equal amount of everything, then the one that is so you see here the mass of methane is the one that is the lowest, all right, and it still give you a lot of heat. So if you use the same mass, then methane will give you the largest amount of heat, right? So most heat is going to be methane, all right. And if you use the same mass, then um, acetylene will produce most carbon dioxide. Oh wait, oh we have to scale. We have to do the calculation. My bad. Sorry. Here we have to do the calculation. Um, so we have to scale it to 200 grams of fuel. All right. So 180 grams. Um, let's do the calculation. 180 times 200 divided by 495. So it's going to be, oh, sorry, 180 divided by 200 times 495. Sorry. Wait, it's weird. Wait. My bad, my bad. Sorry. 180 grams of methane will give you 495. So 200 grams here. Oh, 200 times 495 divided by 180. Sorry, my bad. What? 200 times 495 divided by 180. So it's gonna be 550 grams if you use 200 grams of methane. Um, 199 is almost 200, so it's gonna give you this much of CO2 and acetylene here. Oh, this is the smallest mass of carbon dioxide. Okay, my bad. The smallest one is also methane, all right, based on the calculation. Okay, I read it incorrectly. Question number 14 is going to be A. The smallest amount will be this one because you can see here, you can do the calculations, kind of scale up to 200 grams, and then you see that methane is actually produce the smallest amount of carbon dioxide. Okay. Moving on to 23 and 27. The active chemicals of the head of the match have KClO3 and we have P4O B4H3, heat friction will light up the match. Which of the following is the best reason why chemicals were chosen for the making head? Um, you need to have something that can make the head explode into flame. All right, cause a small explosion. All right, you need to have the explosion to kind of light up the match. Um, wait, this is correct, but like let's take a look at the other one. Sick well, no, both solids. Release oxygen when heated. Then this one can react with oxygen. Okay, this one is also correct. So let's take a look at the all the information one more time. Yeah, explode into flame. Oh, the explosion is because of friction. Okay, it's because of friction. So this is probably not as correct as the option B. So when you heat up potassium chlorate, which is that one, when you heat it up, it's gonna give you potassium chloride and oxygen. All right, this one will be burned in before S3. All right, and therefore it can maintain the light. All right, so it's gonna be B. Sorry, my bad. So 23 is B. Question number 27. When a piece of wood is burning, heat generated from flame heated burn wood. The heat burning causes the flame vapor from the wood to catch fire. In this way, the flame will spread. Okay. The best name for the whole process of obtaining samples of these vapors would be uh okay, let's see. We have a piece of wood, you have the flame, heat unburned wood causing more flammable vapor to distill out the unburned wood, and then you cool down flammable liquid, collect here, and the gas escape. All right, this is called distillation. All right, based on the setup, you heat up something to vaporize everything, and then you have one process to kind of like condense it. Use a cool tube. So that is basically um the distillation process. A distillation process is when you heat up something over here and you kind of deliver everything via a tube. All right, kind of deliver everything via a tube. You're gonna need to kind of lower the temperature of that tube. All right, so whatever things that you can collect in the liquid state, it will condense. The rest will be gas that will fly out, and you want to kind of collect the flammable liquids. So it's distillation. All right. For condensation, all right, condensation only be applied in the Kunst tube, but it will not be able to explain why we heat up over here. All right. So for distillation, it can also kind of like include condensation as well. For distillation, you're gonna heat up on one side and condense on the other side to collect the thing that you want to collect. All right. Combustion is not for figure two. Combustion is the first process to kind of like to kind of burn it. All right. So, but here you do not burn it. You just want to heat up so that you will evaporate all the liquid, flammable liquid, and also some of the gases. Okay. So we liquefied it. Therefore, it's not going to be combustion. Combustion is the reaction with oxygen in air to burn it. Evaporation, yes, evaporation is correct over here, but it will not include the condensation on the right hand side. So basically, evaporation and also condensation are both used in the system distillation. So distillation can cover the whole thing. Okay, and that's it for today. Do you have any other questions? If not, then we finished. Thank you, everyone. All right, I don't think that you have any questions, so then you can run with the class here. All right, see you guys.